Hello everyone! In my last video I tested the first prototype of my ESP32 based BGA Rework station. The software was working great. Both the top and bottom heaters responded correctly, but the setup was still rough and not very clean. So for this video I decided to take the project to the next level and make everything look much more reliable. For the improved version, I completely converted my old Lenovo PC case into a full BGA Rework machine. Here's what I changed and upgraded. This upgraded version of my DIY BGA Rework station includes several major improvements that make it far more stable, accurate, and professional than the earlier prototype. In this upgraded build, I added a complete physical control panel to make the whole BGA Rework process easier and safer to operate. I installed dedicated LEDs to show system status, along with start and stop buttons to begin or end the reflow process instantly. For emergencies, I added a kill switch that immediately shuts down all heaters. Along with the hardware upgrades, the software has been refined with a better web interface that displays live temperature graphs, supports fan control, emergency thermal cutoff, and full automated reflow profiles. Overall, this version looks cleaner, functions more accurately, and gives me a much more powerful and reliable BGA Rework setup. You can achieve reliable results without expensive professional equipment. I cut an empty can to use as a housing for the emitter bulb heater, which gives good results. However, I found that a hot air gun works better for sensitive chips like GPUs. So in this video, I'll be using the hot air gun nozzle for better control and safety. I even converted a metal pipe into a rigid arm for the top heater and securely attached the hot air nozzle for precise alignment. To support the board safely, I built a strong adjustable metal frame that can hold either an emitter bulb heater or a hot air gun nozzle, giving me dual heating options depending on the chip type and reflow profile. I designed and handmade a custom PCB holding stand that keeps the motherboard level and prevents warping during high heat. For the wiring, make sure to use high-temperature cable sleeves on all main power lines, and use high-temperature silicon for any exposed sections to prevent electric shock and short circuits. Add a ground wire to the case for safety. If your setup generates a lot of internal heat, you should also install a cooling fan inside the case to keep everything safe. In my build, I monitored the temperature inside the case during operation and noticed that the heat level stayed normal, so I decided not to add a fan. But you should always check your own setup and add one if necessary. I also designed a custom PCB to make the whole build more professional and clean. With the PCB, you need far less wiring, and everything becomes more organized and reliable. However, if you just want to keep things simple, I would actually recommend using a breadboard. Only move to a PCB if you already have experience or if you want to learn the process. PCB etching is a completely separate topic on its own. You can use a laser jet printer and toner transfer method, or you can do it the way I'm doing it in this project, by drawing the schematic directly on the copper board using a permanent ink marker before etching. GPU and PCH chips are very sensitive to heat. Too much heat for too long can destroy them, or cause visible issues like bubbling. Let's talk about thermocouples and software profiles, which are very important because the entire system depends on them. The actual temperature of the target chip during the process is critical, and placing the thermocouple in the right spot is essential. There is no size-fits-all answer for profiling, as it depends on many factors such as heater wattage, how fast heat transfers to the PCB, the distance between the heaters and the PCB, and whether you place the bottom sensor under the PCB on top or directly on the heater. If you use a sensor on the heater instead of the PCB, you must calibrate the actual PCB temperature with many test runs. The downside is that you won't get an exact reading of the PCB temperature, so you need to observe at what temperature the solder joints melt to fine-tune the profile. Using a sensor directly on the PCB is simpler, but you must always ensure it makes proper contact and verify the readings carefully. This system works according to your inputs and calibrations. If it's not working as expected, focus on getting accurate readings and refining the reflow profile through multiple tests on scrap boards. I also added a third independent temperature sensor that can be placed anywhere, on the top heater, bottom heater, PCB edge, or near the chip, to monitor real-time temperature without affecting heater control. If you don't want to use a software profile, you can simply set the preheat stage to 5 to 10 minutes and manually control the heaters using the buttons while watching the temperature readings. This allows you to do manual reballing while still monitoring the thermal conditions safely. There's also a manual fan control button, plus separate heater control buttons for both the top and bottom heaters. I included an additional button that I plan to use later for features like a vacuum air pump for lifting BGA chips safely after reflow.